Hello, I am Woong-Kee, Gachon University, South Korea. This is the secondary session of the 2021 Annual World ABC Forum. We have three speakers today. The first speaker is Professor Elisa Bertino, Purdue University, USA. And the title of our talk is AI-powered network security. Elisa Bertino is Samuel D. Colt Professor of Computer Science at Purdue University and Research Director of the Center for Education and Research in Information Assurance and Security, CERITAS in short, an institute attached to Purdue University. She received her PhD from the University of Pisa, Italy. She is a fellow of IEEE, ACM, and AAAS. She received the 2002 IEEE Computer Society Technical Achievement Award, the 2014 ACM SIG SAC Outstanding Contributions Award, and the IEEE 2021 Innovation in Societal Infrastructure Award. Now I'm going to play a presentation video. Wait a second, please.
Hello to everyone. I'm very pleased to be part of this forum and sharing with you my view on the use of AI techniques to enhance network security. Networks have seen major advances, mainly due to advances in wireless networking. Wireless networking has seen explosive growth and continuous evolutions over the past decade. Four-generation long-term evolution, cellular technology has increased the bandwidth available for mobile devices, in essence delivering broadband capacity to those devices. 5G new radio is further enhancing the transmission speeds and cell capacity. Technologies continues to advance rapidly, however, and the next generation, 6G, is already being envisioned. Next generation's applications of wireless communications, which are often mentioned by analysis and case studies, are from a diversity of domains, including human communications, various forms of Internet of Things, manufacturing, and even chip-to-chip communication. So we can see from those application examples, the latency will be a critical requirement. Also, next generation wireless networks will be more about connecting devices, robots, autonomous systems, rather than just humans via mobile phone. Data that you can see in the slides show, as of September 2021, the year-to-year growth rates of cellular connections in 2020 and 2021. Supporting the many envisioned applications will, however, increase the complexity of next-gen networks. Also, those networks will be part of even more complex network systems. An example is represented by space-integrated networks, in which a terrestrial internet and wireless communication system will be integrated in space-based networks. However, complexity of devices will also increase as more and more wireless technologies are introduced in those devices. Today, mobile phones support 4G LTE and 5G, Wi-Fi and Bluetooth. However, other technology may be added, such as satellite communication, Wi-Fi with gigabyte capacity, also known as 60 gigahertz Wi-Fi and light-based communications. And what is important to mention is that each such communication technology has its own use cases. Also, many more actors will be present in the wireless communication ecosystems, including conventional mobile network operators, MNO, virtual MNO, virtual mobile network aggregator, mobile virtual network enabler. In this context, there are even more recent proposals, such as the notion of broker, introduced recently by paper by Professor Schenker by Berkeley. In addition, we can expect private cellular networks set up by organizations, mainly for security and privacy reasons. A very important requirement across those complex ecosystems is a seamless experience for end users and devices. Users should be able not to notice changes in the actual wireless communication technologies, which is used while they are communicating over the network. Of course, unfortunately, complexity is the enemy of security. Just a couple of examples. The first focuses on security issues due to mechanisms used to support the coexistence of different wireless communications. This coexistence is critical for performance, but introduces side channels. An analysis carried out on a combo chip has identified several vulnerabilities. See the list of CVA in the slides. An example of vulnerability is the one where the attacker reconfigured the serial enhanced coexistent interface, SICI, via Bluetooth by writing FF as a configuration to a certain register. This causes a voltage drop from 3.3 logic to 17 volt. The drop then halts the processor communication with Wi-Fi and also causes kernel panic on various devices. And another example, which this is from our own work, is related to protocol and specifically to the voice over LTE protocols and the voice over Wi-Fi protocol. We observed that for certain phone models, when voice over Wi-Fi is being used, attacks to the voice over Wi-Fi prevent the phone from receiving calls on voice over LTE. Even one would expect that having two different wireless communication capabilities would allow resilience to attack. The reason for this problem is that when a voice over Wi-Fi is used, the phone does not execute the paging protocol on the cellular networks. We can expect additional vulnerabilities to be introduced when more communication technologies will be added to the devices. The main problem is not really when humans are communicating, but the problem will be critical for applications where the communication parties will be devices such as IoT devices, robots, etc., with real-time requirement, and those applications may not tolerate delays. We need to add the vulnerabilities of cloud infrastructure used to support current and next generation networks. Also, the increasing in network softwareization, that is the implementation software of many network functions, will bring with it all the security issues of software and the supply chain. So what can we do to address security? Well, first of all, we need to have a good security, network security foundation and adopt a network security lifecycle. And AI, machine learning, and big data play an important role in both those important directions. Let me first talk about network security foundation. Identifying what are the foundation of network security is challenging, and I'm not certainly trying to do so. However, from my point of view, one should at least make sure the network protocols and their implementation are free of vulnerabilities. It is important to notice that those protocols are multi-steps, stateful, and involve multiple parties. To address this problem, we developed an initial systematic methodology that we use to analyze the non-access stratum of the 4G LTE wireless protocol. However, and this methodology requires to provide an abstraction of the protocols in terms of finite state machines representing the communicating parties. For example, as you can see in this diagram, the UE state machine, which represent the protocol from the point of view of the cellular, of the mobile phone, and the core network state machine, which represent the protocol from the point of view of the core network. In addition, we add an adversary in this model. The adversary will try to do attacks on the communication channels to prevent the correct termination of the various procedures of the protocol. And once we instrument this model, we then provide this instrumented model to a model checker together with relevant properties from the standard to detect malicious scenarios. Those are scenarios in which the correct conclusion of the protocol execution is not reached, and therefore those may indicate attack scenario. Now, what is very important to notice that applying such a methodology requires addressing several challenges. One is to extract protocol abstractions in form of finite state machines from standardization documents, which are written in natural language. In our work, we did this extraction manually, but automatic approaches would be required. And this poses very interesting challenges for machine learning techniques for processing natural language documents. However, what is critical is the ability to really generate those at least semi-formal specification. This will not be trivial. The other challenge is to extract such abstraction from protocol implementation. For example, to verify compliance of the implementation with the standard. The problem here is that the model is extracted from an implementation is very large and therefore cannot be used for formal verification with the currently available tools. And therefore, we need machine learning techniques to enable us not only to extract these models from large code bases, but also to prune those models. And therefore, we need to come up with suitable techniques. From the life cycle point of view, it's very important to mention that a lot of attacks are due to misconfiguration of security tools such as firewalls and poor management of security. And it is important to mention that even the best security system may still be attacked for various reasons. So to achieve effective protection, we need a comprehensive security lifecycle management, which includes not only to prepare and prevent the attacks, but also continuously monitoring the protected systems and then when anomalies or attack signs are detected by using those monitoring techniques, one has to execute a diagnosis, detect the attack point, possibly predict the next steps of the attack. Then one has to block or contain the attack, bring back the system to its normal state, etc. Here, there are a lot of many opportunities to use AI and machine learning techniques, but they have to be tailored to networks. A very interesting example in this direction is the combination of two machine learning models to predict attack, to protect against denial of service attacks to a certain function in a core network or wireless or 5G wireless systems. So one model predicts signaling workload. So this model will observe the messages being exchanged and will try to predict that certain flows may lead to a certain workload. And the other machine learning model determines if the predicted workload has anomalies. And this is very interesting because it will basically allow one to anticipate much in advance a potential denial of service attack. But again, it has to use two different machine learning techniques, each one with a specific function. The other technique, which is very interesting, is the use of reinforcement learning to slow down potentially malicious flows. This is the case where typically a network the controller of the network will analyze flows of messages or packets being transmitted across the network, and may, by analyzing those packets, identify some flow as a potentially malicious. However, in some cases, in order to be sure that the flow is malicious, one has to observe more of those packets. So here the strategy is to slow down the flows, which may be potentially malicious, so to be able to do a correct diagnosis. This is very important in order to prevent false positive. That is, by to prevent the someone, the network controller to identify as malicious flows which are really actually benign. But those are just some examples. Now I want to discuss briefly about some project that we did in the context of this area, and we came up with a framework for learning attribute-based access control policies. It is very important to mention that those policies will be increasingly relevant for networks. The reason is that recently there is a lot of emphasis on zero trust architecture. The idea of this type of zero trust architecture is to deploy a lot of controls to make sure that malicious insiders or attackers who have been able to get inside of a network cannot perform, for example, lateral movement across the networks, and therefore this requires micro-segmentation of the network based on access control policies. And what is very interesting to mention is that there is a NIST document which identifies the architecture and mentions that policies used in zero trust architecture will be attribute-based access control policies. Now, those policies are based on the idea that the policy, also called, let's say, a rule, is specified in terms of conditions against attribute of the subject requiring access, the protected resources, and also possibly on the context. And those are specified in terms of attributes. Okay, so here, for example, we can see an example where a policy says every user who has a deposition security manager can read all documents of type crypto report. So this is a very high level policy, which is very interesting, because typically when a subject changes the position from the administrative point of view, we don't need to revoke permissions. We just need to modify the attribute of the subject from changing the position from security manager to the current new position. So those are very powerful, and actually ABAC has also been standardized by NIST. And we envision that this type of policies will have an increasingly important role in ensuring network security. However, the problem of learning those policies is not trivial. The reason is that we will need to deploy a huge number of such policies, and coming up with those policies manually is not feasible. So here is an area in which machine learning can help a lot. In this project, we therefore came up with an approach to learn those policies from data. And today it's very easy to collect those data because typical organizations log everything. So every messages, every data accesses, and so forth. However, coming up with an approach requires to use multiple machine learning techniques. So for various reasons. The first was that those policies that we needed to get as a result have to be in terms of rules. And those rules, as I have shown before, must include the predicate against the subjects and the protected resources. And also it's very important to be able to leverage possibly additional data resources that an organization has in addition to logs of past access control decisions. And so for this, we came up with a pipeline in which 4 different techniques are used in the generation of those ABAC rules. So the first step is a conventional association rule mining. We use one of the most famous off-the-shelf techniques. So the first step, we generate those rules using association rule mining. The main problem with the rules that we obtain after the first step is that they are overfitted, and therefore they may not generalize very well. So the second step execute some generalization of those rules. However, the generalizations has to be carefully executed in order to avoid excessive generalization, which may be dangerous from the point of view of the security. Then we have a third step where we add explicit negative authorization. This step is only useful when one has an access control model that supports not only positive authorization but also negative authorization. Finally, we augmented the rule using machine learning techniques. This is very interesting because step two execute a generalization based on structural information, typical organizational chart available and other information such as information in directories. The fourth step generalizes using similarities. So, and we did experiments on a very large data set of access control decision, which was made available by Amazon by a KDD competition of several years ago. This data set has more than 700,000 decision examples. So we did 2 different experiments. The first one was a subset of the Amazon data set in which we trained and used this based on Woong-Kee decision examples. And therefore, you can see the score. But then we also trained our model using the entire Amazon decision example. As you can see, of course, when we use the entire Amazon data set, we basically have excellent results. Both the precision, recall, the F1 score, accuracy, they're almost equal to 1. Of course, when using a smaller sample of Woong-Kee, on certain metrics, we don't do very well, but still the metric is acceptable. Okay. So this means that the policeman is very effective. Now we also have some other experiments where we use only positive authorization. The reason is that negative authorization may not be used in certain application domain or certain context. Notice that when we use only positive authorization, even on we did this experiment on the Woong-Kee sample, we get a very good result. This indicates that in general we have a less good result for negative authorization, when negative authorization are present. And the reason is that when you have a negative authorization, we tend to basically deny more authorization to users who have actually the right to access the data, which from the security point of view, this is quite fine because you want to have an error more on the safe side, But only when dealing only with positive authorization, the metrics are very good. And the reason was that the Amazon data set did not have a lot of negative examples because usually those do not arise in practice a lot. So this is the end of my talk, and let me know if you have questions.
If you have any questions, please turn on the microphone and ask questions.
Hello, my name is Professor of Gachon University. Can you hear me, please?
Yes.
Okay. And I heard that you are very wonderful presentation, and thank you very much for the present of your research result. And I'm very impressive of your presentation, and you explained the Prisma method, and there are four kind type of rule mining and rule generation, rule augmentation using domain or rule augmentation using machine learning. So after the finish the pipe, after the finish the pipeline, we can get the good rule, right? And
Yes.
yeah, and you said the result of experiment, even though the negative example are few, because of negative example are few, therefore they are not sufficient in improving the learning of negative authorization. That means if the data set have the enough of the negative example, so we can get the good result of the learning of negative authorization, something that.
Yeah, basically what we found when we also did the experiments with the negative authorization is that we give a more negative authorization, which means that we obtain more negative authorization, which is good in a way, which means that, so the errors, let's say the lower accuracy for negative authorization is due to a larger amount of negative authorizations which are obtained by police, which means you deny more than you should. But for security is good, because for security, you prefer to deny more than to allow more. So in this case, it's okay to have a more negative authorization. It would have been bad to have a more positive authorization. So a system which gives you less positive authorization and more negative authorization is better than a system where you have a more positive authorization that you should have and less negative authorization. So that was the result. What I want to mention also, which I didn't say during my presentation, when looking at these 4 stages, we did some measurements to see how accuracy was after the initial step. Accuracy was very low, was about 0.5. The second step, which generalizes the rule, increases accuracy. And the last step, the machine learning, also increases accuracy quite a lot. So they are all needed because each one adds some knowledge. And what this shows that you can extract knowledge not only from data, but also from logs, but also from other sources. And enhancing rules, you can look at by similarity. So we say there is an access which is similar to another one, so we can use the same rule for both of them or generalize the rule. And you can also say, I can use a structural information, which is more looking at hierarchies of users, hierarchies, for example, of machines, and so forth. So those will be equally important to have good policies.
Thank you very much. I have one more question, please.
Yeah.
You mentioned that almost 3 machine learning model. One is the one model predict signaling workload.
Yeah.
Second model is determine if the predicted workload was anomaly or not, something like that.
Yeah.
And the finally model is the reinforcement learning, and using the reinforcement learning to slow down the potentially malicious flow, right?
Yeah.
And yeah, and would you tell us if any particular off-the-shelf algorithms have proven more successful than others for network security purpose?
Yeah, actually, these two examples are two different, done by two different groups. The first one, where you use two different models for predicting the flow, and then looking at this prediction and say this predicted flow will be likely malicious, is done by a different group of people from Canada. If you send me an email, I'll send you their paper. It's very interesting. So you can see the type of machine learning techniques they have used. The last example is from our own work. The idea would be that you want to have a good quality of service. So you want to deliver those flows very quickly. Now, if you use a conventional approach, this conventional approach will look at single packets and may say, oh, this flow is malicious. In our case, with reinforcement learning, we can look over the past. So we kind of analyze, sequence of packets, and we can reduce the number of false positive, which says, a false positive means that you classify a flow as malicious where the flow is benign. So for us to observe more, more of a certain flow, to observe more packets, we need to slow down the flow, because if this flow is a denial of service attack, but you are not sure it is really a denial of service attack, if you stop the flow and then the flow is really benign, you create a false positive and the user will lose data. But you cannot let the flow go. So when you have a certain uncertainty, you can slow down, and at a certain point you can have more, let's say, points to judge the flow. We did experiments and this worked very well. That's where reinforcement learning is good, because it's kind of a very interesting technique where you can decide actions, see the reward of the action and change your strategies. We have a paper on that also, so I can send you the paper.
Okay. Thank you very much, Professor Elisa. Thank you for your kind answer, and thank you. Very nice
talking to you.
Thank you.
There is one person who raised his hand, Dr. Yahawi.
Thank you, Professor. Thank you, Professor Bertino, for your presentation. It was nice. I have two questions. The first one is about the data set. You have some kind of imbalanced data set, and generally there are some techniques to balance the data set. I don't know if you used some of these techniques to make them balanced. My second question is about the volume of the data. You have a huge volume. You are talking about the past. You are talking about tracking the logs for DDoS attack and so on. Did you think about data reduction techniques? Because now, as you know, the convolutional network, the deep learning network comes with a reduction power. And in the heart of these ML technique, the reduction plays an important role. At the same time, reducing the volume and not losing at the accuracy level. So this is my second question. Are you using kind of data reduction in your work?
Thank you. This is a very, very good question. For the techniques to make the data set more balanced, we are aware of those. We did not use them. Okay, certainly, those can improve the accuracy. From our point of view, again, in our case, because of what I explained before, having a few training data with negative authorization
from the security point of view was not a problem, because again, we with those few, we generated more negation than we should have, which does not undermine security. It may undermine availability. A certain user may not be able to access. But certainly, I agree with you that using those techniques, one can do better. Our point was more to show that you need a pipeline and use a different techniques which can bring a different type of knowledge when you generate those rules. And again, which a single machine learning technique may not be enough in general, in our context. Concerning data reduction, that is an excellent point. Now, for policemen, we did not have this problem in the sense that those rules are defined quite in advance. So you have an administrator would have plenty of time to generate them. It's not that you have to do this in real time. For real-time cases, when your system changes a lot, and in future networks, this may be the case where you have to continuously change your configurations, then having real-time approaches which are fast will be critical, and perhaps data reduction would be very relevant there. So think the case in my pipeline where you have detected an attack. Okay, so you have to isolate a portion of your network, which means you need to rapidly deploy rules preventing access to that network. In this case, you may have to generate them dynamically, and then you have to be very fast. And definitely, you may not have a lot of data. You may have data, but you have to process them very quickly. We haven't worked yet on doing approaches in which you can dynamically reconfigure the policies for your network, but that is in our research agenda to do.
Thank you. Thank you.
Professor Bertino, I would like to ask one question. Thank you very much for your wonderful talk. I am wondering if the policeman system could be applied to security problems other than attribute-based access control. For example, intrusion detection. If so, is there any need to change the machine learning algorithms in the policeman system?
Well, actually, policeman would not be, as it is, a good fit for example, intrusion detection. Typically, because usually policeman was designed to obtain rules. So at the end, we wanted the symbolic knowledge, not something which is, and that's why we couldn't use deep neural network from the beginning. Because at the end, you have to come up with those rules, like if age is greater than 18, then you give access to a certain file. So we needed really this, what is known as a symbolic knowledge, not sub-symbolic knowledge. For intrusion detection, there is a lot of work and which uses deep neural networks of various forms. And usually there, I haven't seen the use of, for example, symbolic knowledge combined with the sub-symbolic knowledge extracted from data typically. But that could be interesting. But again, a policeman is usually good whenever you need to come up with rules like firewalls and so forth.
Okay. Thank you very much for your answers. Is there any question, audiences? Okay, then we will proceed to the second speaker. The second speaker is Professor Jung, Gachon University, South Korea. And the title of his talk is Applying Deep Learning to New Vision Sensors for Extreme Imaging Conditions. Jung is a professor in the School of Computing, Gachon University. He received PhD from Korea Advanced Institute of Science and Technology, KAIST, in 2005. From 2005 to 2010, he was a principal research scientist with the Samsung Advanced Institute of Technology. From 2014 to 2015, he was a principal engineer with the System LSA division of Samsung Electronics, contributing to the development of image sensors and multi-camera solutions. I'm going to play his presentation video.
From Gachon University in South Korea. It is my pleasure to have an opportunity to present my research work in this World ABC Forum. So here I will talk about applying deep learning techniques for computational photography to new vision sensors. First, I will review recent deep learning approaches for computational photography to improve the image data quality. Then I will talk about applying such deep learning techniques to new vision sensors that can provide better image quality for low light conditions than conventional image sensors. Recent convolutional neural networks have shown outstanding performance in generating visually plausible image contents for various low-level vision tasks, such as image super resolution, the image inpainting, the colorization, or the high dynamic range imaging, etc. So we can improve the image data quality by solving image restoration problems using deep learning techniques. As shown in this example, the deep learning can synthesize the colorful image from the input grayscale image, and it can also restore some corrupted input images. Encoder-decoder network architectures have been widely used for this kind of image-to-image synthesis task. This network consists of several convolution layers with spatial downsampling in the encoder part to extract the meaningful deep features, and the extracted deep features are reconstructed from high level to low level by convolution operations with spatial upsampling. In the final up layer, the network provides the final high-quality images that we want to obtain. I'll briefly review the state-of-the-art deep models for some image synthesis tasks. This slide shows an image-to-image synthesis problem for synthetic depth of field effect. The current smartphone cameras use a fixed aperture size so that it cannot change the aperture number. This means that the camera cannot adjust the depth of field by altering the aperture size. However, the users sometimes want to take a portrait photo with shallow depth of field. As shown in the right-hand side image, only a part of image is in focus and the background is blurred. The recent deep models such as the ECCB 2020 challenges models provide promising quality for synthetic bokeh effect. Two stacked encoder-decoder networks with skip connections are used for the image generator. Also, two patch GAN discriminators with different static fields are used to improve the quality of the generated images as adversarial loss for training the generator. Eventually, the network can provide visually plausible depth of field effects without explicitly estimating the scene depth information. Here is another example of a deep model to acquire high-resolution images from multiple low-resolution images. This is known as super-resolution techniques in computer vision. The specifically burst super-resolution method takes several low-resolution images with short exposures, for example, 4 images taken by pressing a camera button. And then the multiple low-resolution images are merged into a high-resolution image. This deep network is also based on the encoder-decoder network architecture. It has several encoders to extract the deep features from multiple low-resolution images. Here, the key technical issue is the feature alignment to reduce unwanted visual artifacts in the final merged images, such as visual ghost artifacts. So the network contains a flow-based warping module to align the feature coordinates among the multiple images. And then the aligned features are merged by using a tension-based fusion mechanism. Finally, the fused deep features are decoded to output a high-resolution image. Another example is image and video in painting. The cropped image is prepared by freeform image in painting method. And the in-painting method can be applied for object removal that can lead to unwanted regions at the photo editing stage in smartphone app. In addition, some objects in the given video can be removed by tracking and in-painting the video object. Many existing methods for image in-painting are also based on the encoder-decoder network. For example, two-stage encoder-decoder is used in the recent work. The first stage network tries to recover course structure information, and the second stage refines the course output from the first stage. In training the model, the discriminator tries to classify the network output as real or fake, so the model can learn to generate the realistic in-painted images. Similar to the image in painting, another example is hint-based image colorization. In this task, color hints are given in prior. For example, some hints are given by users scribble in an editing tool. The deep learning model can learn how to propagate the given color hints to reconstruct the colorful images as natural as ground truth images. This figure shows that an encoder-decoder based deep model reconstruct correctly the colorful image from grid color hints. More interestingly, the deep learning-based colorization model can reconstruct visually plausible color images from even 1% random color hint pixels. Here the color hints are very sparse and located at random positions. But the model can properly propagate the given color hints by learning the low-level and the high-level semantic features. Here is another example result for the natural image. We can see that the dim model can properly reconstruct the colors for whole pixels from just 1% sparse color hints. Considering that recent deep learning models can provide promising results for computational photography, during the past few years, the smartphone industry has been trying to deploy such deep models into smartphone cameras in the photo shooting stage or the post editing purpose. However, this simple deployment of deep model cannot dramatically overcome the limits of current cameras. For example, the current image sensors cannot provide high-quality photos in extreme imaging conditions, such as very low light conditions or the high dynamic range imaging conditions. What can we do in the next? Maybe we can try to make new image sensors that are better than the conventional cameras. Here I will introduce a new type of camera which is inspired by human vision and can provide better imaging quality. Specifically, I will discuss a novel concept of peripheral vision sensor which uses deep image colorization techniques for better low-light shooting performance than the conventional Bayer cameras. Most conventional image sensors use RGB color filter array on top of photodiode. The incoming light is filtered by the color filter and converted into electrical signal by photodiodes. Surprisingly, the Bayer color filter array has been used for more than past 40 years. The Bayer color filter consists of 2x2 mosaic pattern with 2 greens and 1 red and 1 blue pixel. However, Bayer sensor has critical problems in imaging because of low quantum efficiency due to Bayer filter. The color filters on top of the pixels observe and reflect some portion of the incoming light. So only around 50% of the light photon is converted into electrical signal. This causes imaging problems on low level of signal-to-noise ratio. If we remove the color filter, the quantum efficiency increases up to 76% in this example product. Removing the color filter is good for some imaging quality like SNR, but in this case we can only capture monochrome the pixels without color. Unlike the image sensor, human eye has two types of photoreceptors in the human retina. The one is cone and the other is rod. The cone cells are mostly located in 2 degrees foveal vision area and responsible for color vision and tuned for bright lights. In contrast, the rod cells are mostly located in peripheral vision area and responsible for brightness perception and tuned for low light conditions. As you can see in the figure B, the peripheral vision consists of very sparse cones and dominant rod cell. That is good for the low light condition. Bayer CFA fixers look like cone cells in foveal vision area, as seen in the previous slide. Each pixel captures color information. Why don't we make a new sensor that looks like peripheral vision in the human vision? Such peripheral vision sensor dominantly capture luminance but sparse chrominance as shown in figure B. If we make such a sparse color sensor, we need color reconstruction method in the later image processing pipeline. Why not? We have already seen the reconstruction power of the deep learning based colorization model. The traditional image processing algorithms cannot properly reconstruct the color from the sparse color. Even for 50% the color hint, the traditional approach cannot recover, but deep learning can. In order to prove this concept of peripheral vision sensor by applying the deep image colorization model, we constructed an imaging system that consists of one color camera and one mono camera. Here, the mono camera do not have any color filters, so it has a higher quantum efficiency than the color camera. The two cameras are optically geometrically aligned by using a half mirror and software warping algorithm. Then we sampled 1% color pixels from the color camera and the remaining 99% monochrome pixels from the mono camera. Now it's time to reconstruct a full color image from 1% sparse color and 99% monochrome pixels by using the dim image colorization model that I introduced in the previous slide. Look at the reconstruction result in figure C and compare it with the ground truth in A. It's almost identical to the ground truth. Here is another example result reconstructed from 1% sparse color pixels. The reconstructed image in figure B looks like the ground truth image shown in figure A. And the zoomed version, you can see that these images are almost identical. Quantitative comparison results also reveal that the proposed deep colorization model outperforms the existing non-deep learning or the deep learning methods. In terms of color PSNR and the color difference measure between the ground truth and the reconstructed color images, the proposed method significantly outperforms the existing methods. Here is a visual comparison of the two images captured at low light conditions using Bayer sensor and the proposed peripheral vision sensor. As shown in this example, the peripheral vision sensor should show better low light performance because it consists of 99% monochrome pixels that has high quantum efficiency than Bayer RGB camera pixels. Let me conclude my talk. We can improve the image data quality by solving image restoration problems using deep learning. The deep model can correctly reconstruct color images, and hence it allows us to design new types of image sensors. We proposed peripheral vision sensor inspired by human vision, and it can be effective for low light conditions. It could be useful for consumer photography and also automotive or surveillance cameras. In our experiments, the deep learning-based peripheral vision sensor can handle up to 1% sparse color reconstruction. However, the further studies are necessary to realize as a real product. Supervised learning model requires many good training datasets, but it is difficult to collect such datasets. In many cases, we can just collect a limited number of real datasets, and we cannot cover every possible cases. We need to vary training techniques such as meta-learning. Also, we need to investigate which one is the optimal sparse color pattern, and we need to develop new ISP pipeline for the new sensor. In more detail, we may encounter several engineering issues that do not happen in ideal cases. We need to further handle these engineering issues in making a new image sensor as a future one. Thank you for your attention in my talk.
Yeah. Are there any questions?
Hi, I'm Jung Gachon University. Can you hear me?
Yes, we can hear you.
Yes, I can. Yeah, thank you for the good presentations. It's very impressive that you even proposed new sensors. Regarding colorizations, I have a questions. I wonder if there are any failure cases, even though color hints are given well. If yes, could you explain it? What case is the colorization phase?
Yeah, that is a good question. Yeah, so if the color hints are given well for whole the segment regions in an image, the deep model can propagate the color hints where so we can obtain the high quality colorful images without any the visual artifacts. But however, the problems arise when we have the missing the color hints for many small segment regions. Yeah. In this case, the network should learn the semantic features to determine whether the given color hints for a region, they should propagate across the neighbors, the regions. So if we use the enough to train the samples that can cover the every possible case, the network can learn the many semantic meanings and then produce the visually plausible the color image visuals. But unfortunately, in general, we cannot cover every possible the long tail cases in our training data set, due to the limit of the computing resource and the training time. We may have the two approaches to solve this problem. The one way is to make our deep network to be more generalized for unseen data in the testing time. And the machine learning, the researchers are trying to develop the useful tools and method for the generalization of the learning models. Another way is to construct and use the systematic framework for machine learning model production and the management. As I know, the big data engineers can support by making the useful tools for the semi-automatic ML framework, so that the construction of the ML model and the management of the ML model can become easy, as mentioned in the mentioned by the Professor Woong-Kee's the keynote yesterday. Okay, that's all from me.
Thank you for your kind answers.
Are there any questions? Professor Jung, I would like to ask a question. I'm going to convey a question I received.
Yes.
Thank you for your fascinating talk. Your results are very impressive. I cannot tell the difference between the ground truth and the polarization results. You mentioned that it is difficult to get real data sets. What exactly is the difficulty? Is it the types of subjects? Is it the variety of extreme imaging conditions? Some other situations?
Yes. Yeah, as I introduced, that we have seen that during the last decade, if the training data is sufficient, then the supervised deep learning models can provide the very good performance. Especially as I introduced for the low level computer vision task. However, the problem of the supervised learning model is the lack of the good quality training examples. In many cases. For example, in image colorization, in my main test, there could be many different imaging conditions, and the different images can contain the many different the compositions of the different objects in the image. So we cannot cover the every possible case. So also due to the hardware malfunctions, the color hint pixels can be gone. And the bad pixels, so it can generate the false color hints. We need to care about the false color hints. If a false color hint is propagate, then the visual the artifacts will be severe in there. So we need to this is not the ideal case. So but we have to to deal with in the real situation. So actually if we use the enough the training sample that can cover the every possible case in the image colorization, then the deep learning model can learn the many semantic meanings. But unfortunately, as I said, we cannot cover the every cases. So as in my first the answers in the first question, we need to develop the better the machine learning tools, machine learning methods, or the automatic ML method must be supported to make it easy the machine learning the model production pipeline, and including the production and the training of the model and the management of the learning model.
Thank you.
That is my answers.
Dr. Sefinger, please ask questions.
Well, thank you first of all for this fascinating talk. I have actually two questions. So first would be for the color reconstruction from the 1% sparse color. So I guess this assumes that the 1% sparse color is evenly distributed across the image, right? So I guess it will be difficult to reconstruct objects where 0 color pixels have been received. Or is this imputed from the models based on historic data?
So in our simulation, we have the two cases. The one is the random, the other 1%. So the random means is the training in the training image, each training image, the color hint can be located in the random the positions. That is one case. That one case, and then another one is we use the grid, the pixel position. We use the fixed the grid positions. In the cases, every image use the same position, the color hints. We experimented the two cases. In the both the cases, for using the well-known data set, for example, the ImageNet data set, yeah, we obtained the very promising the image reconstruction results from that 2 cases. Yeah. But anyway, as I mentioned, we need to the further work to determine which the color hint, the position is could be better. Yeah. So we need to further work for this. Yeah.
Okay,
to determine
thank you.
yeah.
Thank you. And my second question would be, because I understood you're planning to deploy these deep learning models directly on the camera. So I wonder whether there are any issues with respect to computational power, because deep learning models usually are quite computationally intensive also in the inference because of the huge parameter spaces they have. And so I was wondering, do you have any issues here? And do you look into issues like model pruning to make these models smaller? How is this computational complexity problem addressed in this case?
Yes, yeah, definitely. Yeah, we need to reduce the computation complexity, but then now it's just a proof of concept stage. So I have done much about it work for to reduce the computational complexity, but the later in the deployment stage, definitely we have to do some engineering work for the reduction of the computational complexity by the prunings, etc. Yeah. For example, for your information, yes, currently in my experiments, for example, regarding the inference time of the current the implementation version, for the 1 megapixel resolution image, our model takes the 500 millisecond, for the color reconstruction, so in the NVIDIA the GPU machine, but in order to deploy the models to current the smartphone, very tough. Yeah. But even though the nowadays the smartphone vendors provide the new the processing, the hardware unit such as the NPU neural processing unit, but still is the complex models cannot be deployed easily for that for the other this kind of the other works. But I believe in the soon the hardware will will improve. Yeah. And also,
Okay.
the sensor industry is trying to develop the new the stack sensor. That means it's the current by putting some the logic gate the under the images the picture so that kind of the sensors can maybe save the computation time by providing some low level the convolution operations, for example, or the feature extraction, the processing can be done in the sensor stage, and also maybe the soon the application, the processors can the support in the hardware, and the software could be then I'm optimistic. But we need time.
Thank you so much. That sounds really exciting. So I'm really looking forward to seeing this in my future smartphone. So thank you very much for this work.
Yeah, thank you. Yeah. Thank you for good question.
Thank you very much for your very detailed answers, Professor Jung. Let's proceed to the third speaker. The last speaker is Professor Jian, Simon Fraser University, British Columbia at Burnaby, Canada. And the title of his talk is Towards Trustworthy Data Science. Jian received his PhD from Simon Fraser University. He is recognized as a Fellow of the Royal Society of Canada, the Canadian Academy of Engineering, the ACM, and the IEEE. He received many prestigious awards, including the 2017 ACM SIG-KDD Innovation Award, the 2015 ACM SIG-KDD Service Award, the 2014 IEEE ICDM Research Contributions Award, and 2018 ICDE Influential Paper Award. I'm going to play this presentation video.
Thank you for having me here. I'm Jian from Simon Fraser University. Today, I will introduce my research on towards trustworthy data science. We all believe data science and AI will change the world. Data science is an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from structured and unstructured data. And we also applied knowledge and actionable insights from data across many application domains. Indeed, data science and AI are concepts to unify quite a few different areas, including statistics, data science analytics, data mining, machine learning, AI, informatics, and so on. The whole purpose of data science is to understand and analyze actual phenomena using data. Let's take a look at the end-to-end data science. We have different data sets contributed by different parties. Through data science process, we enabled different applications. And of course, for an application, the most important thing is that it produces value for users. As a byproduct, an application may also produce data, and such data may be fed into the next data science process and empowered more applications. And therefore, the end-to-end data science is a sophisticated, interconnected network. There are several keys in data science. Most importantly, in the whole process of data science, we have different kinds of participants, including data owners, data scientists, and data domain users. Data owners contribute data. Data scientists process data, analyze data, and construct models. Domain users consume models and produce business values. And domain users may also produce new data. And therefore, this loop continues again and again. We are talking about trustworthy data science. Why data science has to be trustworthy? This is an important question. Indeed, an article in the Harvard Business Review says very well. The key skills for data scientists are not the abilities to build and use deep learning infrastructures. Instead, they are the abilities to learn on the fly and to communicate well in order to answer business questions, explain complex results to non-technical stakeholders. Therefore, in the whole process of data science, we need to turn data into effective collaboration, and we need to build trustworthy models, and also the domain users have to produce equal value in the whole system. In order to implement such goals, we need to have effective collaborative learning. We need to have effective interpretation and explanation of models, and we also have to have effective and efficient marketplaces. In the rest of my talk, I will quickly go over these three aspects and introduce some of the work we are currently working on. First, let's look at interpretable data science. What's interpretable data science? Given a machine learning model or an analytic process, how can we interpret to users the model outcome? This question has been encountered again and again in many different domains. For example, in medical domain, when we provide model services to medical people, like medical doctors, they may wonder why the model comes out such a result. And therefore, we want to interpret the machine learning model outcome to those medical doctors. And therefore, interpretable data science is the process of extracting relevant knowledge from a model about the relationships either contained in the data or learned by the model. And here, the knowledge is the insights for a particular audience into a specific problem. In our paper in KDD 2018, we advocate the notion of exact and consistent interpretation. Typically, for a model N, we want to come up with a model M to explain. And we say a model M is an exact interpretation of a model N if M is mathematically equivalent to N. A model M is a consistent interpretation of a model N if M provides similar interpretations for classification or on similar instances. The consistency is a natural requirement for human being, because when our human being analyze data, analyze instances, we try to come up with two examples very close to each other and expect that they may have the similar or related interpretation. With the exact and consistent interpretation, we hope to transfer a black box into a white box. How to conduct exact and consistent interpretation? We take a piecewise linear neural network as an example. Here, a piecewise linear neural network is a deep learning network that where the activation functions is a piecewise linear function. Piecewise linear networks are popularly used in deep learning. For example, those networks using activation functions of max out ReLU are typical examples of piecewise linear neural networks. Our key ideas to provide exact and consistent interpretation for piecewise linear networks is that a piecewise linear network is mathematically equivalent to a set of local linear classifiers. Therefore, given an instance to be explained, we can use the local linear classifiers covering the instance within a convex polytope in the input space as the interpretation. And this interpretation is exact because mathematically it is equivalent to the original model. And it is also consistent because if we have two instances close enough they are in the same convex polytope, they will share the same interpretation. Based on this idea, we built OpenBox, which is an exact interpretation of a PRNN by an equivalent set of local linear classifiers in closed form. And here, each instance can be interpreted using the corresponding decision features. OpenBox can provide good interpretation, exact and consistent, to piecewise linear network. However, it needs to access the model structure, the neural network, as well as the training data in order to provide the interpretation. In many applications, such information may not be available. For example, in the cloud AI, the models are hidden behind the APIs. and therefore a user may not be able to access the model structure or the training data. To tackle the problem, we developed OpenAPI, which is a tool to provide exact and consistent interpretation of PRNN hidden behind APIs. Our approach does not need to access to model parameters or training data. The key idea of OpenAPI is that we find the decision features for an instance to be interpreted by computing the closed form solutions to a set of overdetermined linear equation systems. And then we use a small set of sample instances to construct the equation system. In other words, we perturbate the query instance to obtain a sample of the close to the instance, and we can construct the equation systems. OpenAPI has a very nice property. Theoretically, we guarantee that the exact decision tree features are identified with probability 1. Now, let's look at how people can collaborate in data science. People collaboration in data science is very important. In many situations, there are 3 major types of collaboration. Data collaboration, they share data or they contribute data together to build models. Model collaboration, they share models to build more powerful and better models. And value collaboration, they use different models to form a pipeline to produce the business value. Let's use model collaboration as an example to illustrate. There are quite some challenges in collaboration through federated learning. Although federated learning is regarded promising for collaboration among different people in machine learning, the challenges lie in 2 layers. First, in terms of data, the data from different contributors may not follow the IID distribution. Moreover, multiple collaborators contribute data and would like to construct model. But one global model may not fit all clients. Indeed, one global model may bias on those clients with more data. And also, we want to ensure the privacy preservation and the fairness among clients contributing to the data, to the model, and also the model built collectively. To tackle the issue, we developed personalized cross-silo federated learning. Essentially, we have multiple clients, and then through the cloud collaboration, we jointly build a model. But when we build a model, we don't just build one model fitting all the clients. Instead, every client can also learn from the other clients with similar data, so that it can help to sharpen the model locally. As you can see from here, different from the centralized approach to do the federated learning, our approach, FedAMP, is a privacy-preserving solution that can help to build personalized model. And also, we look at the fairness in model trained by federated learning. We want to ensure that the difference of generalized equal opportunities constraint is satisfied in models trained by federated learning. Here, the challenge is that we do not know how to evaluate the global fairness, because the local fairness may not lead to global fairness. And also, even calculating the local fairness may not be feasible because the data is not IID distributed. Our idea to tackle the problem is that we can use a federated estimation to obtain a good assessment of the fairness. Last, let me talk about the data marketplaces that can enable different users to participate and empower the end-to-end data science as a dynamic ecosystem. In this figure, as you can see, we have many different applications, many different data science process, and produce different data sets. For each user, it may take data from some other applications and parties, and it may also contribute data to support other data science process. And therefore, we want to have a data marketplace so that data and their value can be exchanged. Marketplace is enabled and governed by economic rules. However, data markets are substantially different from the traditional market. But the technology changed, the economic laws did not really change. And still, in data pricing, we still look at the cost, but the cost reduction is substantial for information products. We build Dealer, an end-to-end data marketplace with model-based pricing. In this project, the goal is to build a database for models. And we need to solve a series of problems, including how to price the data models. And the model mechanism will enable us to compensate data owners depending on the preservation of epsilon differential privacy. And the payment of a buyer on a model depends on the coverage of the training data used by the model from all data owners. And the broker will pay a data owner at least what is asked for, and also maintain fairness in the payment among different contributors. We try to minimize the buyer's cost, and also we try to fully distribute all payments from buyers to data owners. So in this quick 20 minutes, I give a very brief survey on the trustworthy data science pipeline, and I talk about 3 different parties: data owners, data scientists, and domain users, and the major process, including the effective collaboration and building trustworthy data models through interpretation and explanation, and also the effective and efficient marketplaces. Indeed, as data scientists, we are holding a lot of responsibility to build trustworthy data science, because the outcome from data science processes may affect many people's lives and the world fundamentally and permanently. And therefore, we as data scientists have the responsibility to ensure the changes are for social good. Such responsibilities include, but not limited to, fairness, diversity, sustainability, privacy preservation, safety, and many. Thank you. I'm more than happy to answer questions here or correspond with you by email.
Are there any questions?
This is Jung, an assistant professor at School of Computing, Gachon University, Republic of Korea. Can you hear me?
Yes, I can hear you.
Yeah. Thank you very much. Yeah, thank you for the talks. And I find your vision of the data science lifecycle and ecosystem interesting. So I have 2 questions. First is, despite of the success of machine learning and deep learning, one of the major issues to address the research is the explainability of the results. It appears that you are proposing to address it with the idea of piecewise linear neural networks. So has your research progressed far enough to establish that it indeed addressed the issues?
Well, this is a good question, and I don't think at this time we are even close to the full capability we wish to have to get the interpretation of sophisticated models. The reason is that a sophisticated model, particularly a deep learning model, you can think about is high level, high dimensional aggregation of a lot of information. Therefore, a good interpretation has to understand this complex structure. And at this moment, we can only deal with simple neural networks, like, for example, the piecewise linear neural networks, or most recently, we work on the things like a graphical neural network, GNN, GCN. And this is far from enough. For example, an understandable interpretation should embodying human experience. And it should also form the interaction between model and users, or model and developers. And those are the areas have not even been touched yet. And also, so far, the so-called interpretation are, for example, polytopes, highly mathematical annotations, and how to visualize such interpretation becomes, it remains a big challenge. And also, we need to engage to the audience, to the users of the interpretation. For example, if I want to produce an interpretation for medical doctors would not like to look at neural networks, right? That's not their domain. They want to have something connecting to them with the, their background knowledge and verifying their findings. And those things are the domain knowledge, engagement to the domain knowledge and the domain experts remained an open challenge. To that extent, I would say we are at a very preliminary step. We are very far away from what we want to be, but that's the direction we are going.
Yeah, thank you very much for your thoughts.
Thank you.
The second question is, it's about the data marketplace. So can you share your thought on the basis of the pricing model and payment distribution model? There are many companies that collect and sell the data, and industries such as the music industry has a payment distribution model for all the stakeholders. I wonder if these have a relevance to your view of the data marketplaces.
Yes, that's a very good question. For the indeed, we are talking about several different things. When we say data, it may mean many different things. For example, the digital products, the data sets, and data services. And recently, I have a survey paper on data pricing, which summarizes and overviews these several aspects. You can find the paper online, and if you want me to send you the PDF file, please just drop me an email, and then I'm more than happy to share with you the file. So when we build a data market, it is important to make sure the market mechanism is transparent, meaning everyone gets the same information, and then there's no inequality in information. The second thing is that we want the marketplace to be fair and efficient, so that everyone can get what it wants. For example, we can make a selfish assumption to say every buyer and seller are selfish, so that we can maximize the market efficiency. And also, we want the distribution of the payment to be fair. For example, satisfying the separate fairness. And how to build such data markets, particularly at a large scale, remains a very challenging problem. One big difference between the data markets and the data product markets in the past is that data products, typically they have well-established specifications, and their utilities are sort of like can be accessible. But for data markets, the value of data sets typically cannot be very well accessed because it depends on the downstream task. And also the specification of products to be sold. For example, data sets can be highly customized and also may change from case to case. And therefore, it is much more sophisticated. To that extent, at this time, we are just at the very beginning of designing good data markets. I see there's still many interesting technical challenges. Yeah, thank you.
Yeah, thank you very much for sharing your thought according to my question. This is the end of my question. Thank you very much.
Thank you.
Professor Jian, I would like to ask one question.
Yeah,
thank you
please.
for your talk. In your work on Fed AMP, you used the BMTA, best mean testing accuracy measure, to compare the performance of Fed AMP with the previous algorithms. Could you please explain why you didn't just use MTA, mean testing accuracy? Are there any big differences of MTA among the results of each training round? If so, what do you think is the reason?
I think, here, if you go to our paper, we have a much more thorough evaluation and comparison between the, on different methods. And here, I just use one example to show the results. It doesn't mean that we have to use this measurement. Yeah.
Okay.
So, yeah.
Yeah. Okay.
Yeah. So we can use other measurements too. They're all feasible.
Okay. Thank you for your answers. Are there any questions from the audiences? Yeah, Dr. Selfinger, please ask questions.
I have a question on the model pricing because I wonder if issues like energy efficiency, because we all know about the issues of climate change that we are facing, and as we all know, deep learning models are often very inefficient in their learning. And should this be factored into in kind of incentivizing people in using smaller, more energy efficient models, for instance, by having a pricing that considers energy efficiency? What is your take on that?
This is a wonderful question. I think that that's a very smart and important idea to explore. So far, we separate the economic mechanisms and the basic costs, shareable costs of the data markets. Essentially, we say, okay, the computation, the model training, all those things would be part of the fixed costs that will be shared among the parties in a data market. And definitely this assumption should be revisited. And as you said, this could be a very important and interesting opportunities to advocate the green environment and also the less carbon emission. So, for example, in the testing phase, in the negotiation phase between data buyers and data owners, it would be important to look at the footprint of their models. yeah, that would be a great opportunity. I don't think this has been systematic or substantially investigated yet, but this is definitely a wonderful idea. Yeah.
Thank you very much.
Thank you.
Maybe I could have a follow-up question because these were so many interesting issues that you were stressing in this talk. And regarding the explainability, I was just wondering, how is your PLN approach related to or different from the local interpretation method LIME? I think it's from Ribeiro and colleagues. So I only was aware from that, and I wondered what are the differences here?
The difference is that the two approach, I mean, for our approach, we from the query instance, we try to find the corresponding decision boundaries to get to derive the local interpretation. But LIME is more or less than they try to mimic the decision, situation. So that's the reason we are more consistent and we are more concise than LIME. You can compare them from the original papers. Another, but you mentioned one interesting, important thing is the explanation. Typically, in this area, we separate two terms. One is interpretation, one is explanation. Interpretation is more from the mechanism point of view. We look at the model and we try to reflect what the model is doing. And explanation, we try to go one step beyond, is that we connect the mechanism with the domain knowledge, with the background knowledge, so that the explanation is expressed using more from the domain knowledge terms, domain experts language. So getting interpretation is just first step. We need to go to the next step to get really explainable machine learning models.
Okay, thank you very much. So definitely need to look into that paper because it's really a very, very fascinating topic. Maybe following up on that, does your approach also give some insights in figuring out why the model might be good or wrong? Because I think models could be perfectly accurate for the very wrong reasons, because I think maybe this was the example in the LIME paper, so which is quite famous when a model was perfect in classifying huskies versus wolf pictures, and then it turned out that it actually only had learned that all huskies were on snow and wolves were not, so it would perfectly fail on a picture showing a wolf on snow, but this simply wasn't in the training data. So is there any mechanism already to kind of get these insights from the models, that, or is this still future work, or do you have any ideas on how this maybe could be addressed?
There are several things we can do. The first is that, if you extract the decision boundaries, you can look at the decision boundary to understand the factors that may contribute to the decisions. This is one idea people are exploring a lot. Another way people may do is that the counterfactual explanation essentially is that we look at the minimal factors that if we remove such factors, the decision will be reverted. And then by looking at what are the factors that may revert decisions, it may give us good, at least good hints to see, well, what the models are looking at. Of course, we do not really look at the I mean, this is not consolidated yet. We cannot say this is 100% the consolidated reasoning, but it at least may give us some hints. Yeah, this is a very good area to work on. A lot of fun. Yeah.
Okay, thank you very much. It's really interesting. Thank you.
Thank you.
Professor Champe, thank you again for your precise answers.
Thank you.
Okay, this is the end of today's session. We sincerely thank all speakers and participants for sharing their knowledge and experiences for AI big data convergence. See you in the 2022 Second Annual World ABC Forum. Thank you.
Thank you.